Welcome to the Horizon Audiofiles, a podcast of the Defense Horizon Journal. The Defense Horizon Journal is a professional and academic journal that features essays, reports, and analyses covering geopolitics and law, security and defense policy, peace and conflict studies, applied military science, as well as developments in weapons technology. For more information, go to www.tdhj.org.
Episode number 47. Additive Manufacturing, a Key Enabler of Low-Cost Modern Warfare. By Wolfgang Müller and Sergej Sumleny. The importance of unmanned autonomous systems in future warfare. Unmanned autonomous systems, UAS, have become critical to war, be it on land, in the air, or at sea. The roles assigned to these systems include reconnaissance and attack as well as support functions, for example, medical applications. Although there are divergent perspectives on their importance, there is no doubt that the massive application of drones will be a part of it, regardless of whether they are decisive in future battles or not. Compared to the use of drones in the conflicts in Libya and Nagorno-Karabakh, the scale and range of drone uses and applications have increased tremendously. Ukraine alone produced 1.5 million first-person view, FPV, drones in 2024. It dedicated $1.2 billion in 2024 for drone procurement, with about $480 million for long-range drones, of which 30,000 should be produced in 2025. For 2025, drone production contracts worth $3.58 billion with a slot number of around 1.8 million drones of various types have been issued. In addition to FPV, air, and sea systems, Ukraine is testing land-based walking drones with its 28th Mechanized Brigade in Toretsk as well as a British model called BAD-1. Other types of ground drones, wheeled or tracked, are also widely used, for example, by the 47th Mechanized Brigade in Kursk Oblast. They are used for multiple purposes: logistics, medical evacuation, laying mines, and mobile gun platforms. In adapting UAS to these roles, the Ukrainian armed forces have elevated drones from a supporting role to a central operational asset. This shift is best displayed in the establishment of the Unmanned Systems Forces by presidential decree in 2024. Of all these systems, 96.2% were produced in Ukraine by local industry. Furthermore, the dependency rate of parts being delivered from abroad, especially from the People's Republic of China, PRC, has been constantly reduced. This reduction is not only due to increasing Chinese export restrictions but also to an increasing lack of reliability, intentional or not. Testament to this is the existence of a 100% Ukrainian-made drone. Ukraine's experience demonstrates that there can be no doubt that drones will play an important role in future warfare. It is also reasonable to assume that armed forces, which rely on expensive winged drones for reconnaissance, artillery, and air strikes, will suffer significant losses against an adversary experienced in drone warfare. It is, therefore, paramount to have the capabilities and capacities to produce the numbers for extensive and long-lasting use of drones across multiple roles. European states, which are not at war nor frontline states, have a certain luxury in preparing themselves not only to defend against but being able to wage that kind of warfare should it become a necessity. Unfortunately, in European states such as Germany, the focus in the past on defense procurement was on quality and technically very sophisticated systems instead of mass production. Today, Germany, and Europe, is unable to produce vast numbers of smaller UAS quickly. Moreover, there is a necessary precondition that is also not met for mass production. Drones, as used in Ukraine, are only slowly becoming part of NATO operational concepts, doctrines, field manuals, and those of its members. Neither NATO nor its members have comparable experience with drones as Ukraine, where mass use is executed at all command levels, platoons, companies, battalions. Nevertheless, the importance of drones in future conflicts demands the capacity and capability to produce drones in vast numbers. The German national security and defense industry strategy as a starting point. The importance of looking not only at technology and doctrines but also at production, both in terms of time and capacity, started in Germany with the strategy paper of the federal government on strengthening the security and defense industry in 2020 to maintain control over technologies that have already been identified but will not be relevant for productive use on a large scale until some point in the future, is essential. In light of the war in Ukraine, the newly introduced strategy of 2024 highlights the importance of a resilient, effective, and sustainable defense industry to be able to draw on sufficient production capacities without delay. To increase economies of scale and enable innovations, we strive to achieve a continuous production of military equipment by the security and defense industry. This strategy outlines the challenges and the must-dos regarding matters of production, both in terms of capacity and agility flexibility. Although this strategy highlights certain aspects of what is and will be of importance regarding manufacturing, the strategy itself offers no clear advice on how to achieve this. Unlike Ukraine, states like Germany have the luxury of being in a position where such drone innovations can be safely undertaken in a planned manner within a relatively reasonable time frame. Additionally, insights from the battlefield can be automatically incorporated into planning and production cycles. This applies to technology, procedures, and processes. Current developments in drone manufacture and use. To identify how best to address the above-described challenge, defense planners need to take a deeper look at the current trends in drone manufacturing. These developments are, until today, not dependent on the outcome of our initial discussion if drones are a game-changer or not. More importantly, strategy outlines like the German one described above, operational concepts like Hellscape, and actual ongoing initiatives like the US Replicator Initiative or the local defense industry initiative, Brave One, in Ukraine are relevant. All of these initiatives show that drones in multiple roles, in different domains and mass numbers will be an element to be considered in future warfare. The developments in drone warfare connected to the production process, starting with Libya and Azerbaijan, and very dominant with current developments in Ukraine, can be summarized as follows. Regarding the number of drones produced and used, it is increasing with no end in sight. At the same time, the use rate of one-time compared to multi-use drones is increasing as well. However, there is an increasing variability both with regard to their roles and the technical modifications. This experience corresponds to the perception of drones as low-cost ammunition instead of mere delivery observer weapon systems. On the cost side, the degressive trend was visible for some time. However, it will most likely peak in the near future because of new features to be added, more stable connection, resilience to electronic warfare, night thermal vision. The production of drones in wartime has changed, shifting from industrial to artisanal, ordinary garage or workshop. Solutions, often crowd-funded. The parts for the drones are mostly available on the global market, and their purchase cannot be limited through export restrictions due to their common utility in various other non-military goods. At the same time, there is a shift from off-the-shelf to tailor-made drones designed for specific needs and tested on a trial-and-error basis, with regular and timely feedback loops established between the producing industry and the military. The next step on its way is the use of artificial intelligence, AI, although still at a very early stage. Initial projects indicate the use of AI for target identification. This is particularly useful amidst camouflage and differentiating fake from real targets. AI is also used in as well as marking and recognition in case of loss of connection to the pilot, most often on the last 200 m. A newly developed model, HX2, from the German startup Helsing should be able to guide drone swarms. Until now, AI has not been used for target selection, prioritization, but this is likely forthcoming. One final trend is notable: more and more separate drone-specific units are being established as units in their own right rather than being embedded within other military units. Additionally, the level of designation for separate drone units is coming down. Drone companies can be found at least at the brigade level, but more and more at the battalion level as well. The establishment of separate and independent drone units, combined with the down-leveling of their attachment, creates new necessities regarding supply chains and local workshop capacities for repairs and modifications. The same logic can be found in other developments, such as the Iranian ship the Marta Barman Bagheri. This is a container ship converted to use as a drone carrier, which can house up to 60 drones. It is valid to assume that modification and repair facilities are installed directly on board. One of the most important aspects is the production costs, where the cost per unit matters for decision makers, as extremely large charges are being discussed. In cost-benefit analysis, the cost-effectiveness offered by drones cannot be denied. The war in Ukraine offers ample evidence of this, such as the sinking of the $65 million patrol ship Sergei Kotov by Magura V-5 drones, costing only $273,000 each. This drone is also responsible for sinking up to 9 Russian ships in total. On land, this cost-effectiveness was seen in the destruction of a $15 million Tor M2 radar unit by a $500 Switchblade FPV. A last example regarding planes was the destruction of a $100 million Tu-22M3 hypersonic bomber by a drone. However, mass production demands a cost-per-unit analysis. Looking at Ukraine again, in the beginning, Chinese off-the-shelf drones from DJI were used for reconnaissance purposes, costing from $1,500 to $5,400, thermal night vision capable. They were used especially to direct artillery fire. At the same time, longer-range drones are used for deep strikes, substituting for the lack of cruise missiles and airborne assets. The costs of those drones are much higher. Later on, with the lack of sufficient amounts of artillery shells, FPV came up in vast numbers. Today, the 10-inch Viri 10 drone costs about $409. The newly developed prototype of a 100% Ukrainian Viri drone costs $503. The prices can be expected to go down, as with the other already existing models in mass production. The most inexpensive drones cost around $200 to $250. Other models, for example, heavier drones used for dropping grenades and mortar bombs, range from $1,000 to $10,000. The basic model of the walking Cyberdog drone costs $1,600. A new application is the use of a winged drone as a carrier for the FPV, which therefore increases their operating radius to 50 to 60 kilometers instead of 25 kilometers before. They serve at the same time as repeater drones for radio signals, which lessens the impact of hostile electronic warfare, EW. Such drones can be bought commercially and cost around $8,000, some of them even less, around $2,700. The cost-effectiveness of these drones is very high, even considering efficiency. The cheapest drones have an efficiency rate of only 10 to 15%, and more advanced FPVs in the range of $300 to $400 achieve a 30% efficiency rate. Even if it needs 20 to 30 less expensive drones to destroy a target, be it a vehicle, a tank, fuel, etc., it is often worth the investment. 3 to 6 drones with a cost equivalent of $900 to $1,800 to guarantee a kill. In fact, more than 2/3 of Russian tanks have fallen victim to drones. Even targeting individual soldiers, who are trained and equipped, is considered cost-effective, as they are much more difficult to replace compared to FPVs. Further, as a pilot has about 40 to 50 minutes of flight time and knows that there is no chance of returning a $500 kamikaze drone once it is armed, the pilot will hit any target over $1,000 or lose the drone. Moreover, the nearer it gets to the end of the in-flight battery capacity drained, the cheaper the price of the target gets. With only 1% of battery power left, anything will be hit to make sure the drone is not wasted. Any enemy target more valuable than $1,000 identified by a drone pilot will be hit without hesitation, as this creates a favorable cost-benefit balance. Additive manufacturing, AM, as a potential contribution. Additive manufacturing, AM, popularly known as 3D printing, is the process of creating an object by building it one layer at a time. It is the opposite of subtractive manufacturing, in which an object is created by cutting away at a solid block of material until the final product is complete. Logistically, there is a substantial difference between the supply chains of traditional and additive manufacturing. The differences between these lead to several potential advantages. Firstly, there are potential savings in developing prototypes. Estimates range to 85% time and 80% cost savings. Second, savings are realized during the production process, be it in the production of prototypes or serial production, as weight reductions, as well as a customized and high-mix low-volume production, can be realized. Additionally, there is higher flexibility through just-in-time production and small batch sizes and higher speed as fewer tools are needed, and on-demand production can take place. A higher degree of customization, a higher degree of complexity, and even a higher rate of repeatability are possible as well. Third, there are savings in the overall replacement costs. This includes shipping and costs attached to the inventory level. Looking at AM for the purpose of addressing military needs, several trends are evident. AM's potential is being looked into by several armed forces, and several pilot projects and evaluations have already taken place. The US has already adopted a fully-fledged strategic approach to the use of AM. Several use cases have shown that mobile AM is possible, even in difficult environments typical for armed forces. Although there are limitations on the accuracy due to transport and vibration resistance, plenty of parts can be produced within acceptable tolerances. There are examples of mobile factories in a 20-foot TEU with a production and a logistical support unit, e.g. scanner for reverse engineering, sometimes airborne capable, e.g. from Xerion on the Enoch AB. The German armed forces operate a modular concept consisting of the so-called EAFE, a light AM unit, AFE, AM unit, VAFE, movable AM unit, and AFZ, AM center. Norway operates a similar concept. Applications encompass expedient repairs, battle damage repairs, temporary replacements, and modifications, e.g. to realize modifications depending on the intended use of existing drone frames. That is why there are already 3D printers in the workshops of every drone unit. However, depending on the purpose for using AM, there are issues of legal relevance to consider because, typically, AM requires scanning the original part to create a CAD file or transferring an existing CAD file from the original equipment manufacturer, OEM. There is relevance regarding intellectual property rights, warranty situations, statutory warranty rights and common liability situations. There might also be issues with export control regulations, as is the case, for example, with the U.S. International Traffic in Arms Regulations, ITAR. Nevertheless, AM has to be considered more strongly for procurements and tendering processes. Common standards, which are aligned with industrial standards, are the basis for common recognition, which is the basis for mutual logistic support. Operational availability of assets has priority, which can lead to a conflict between OEM quality versus functionality. Performance-based, multi-source contracts and the replacement of procurement documents with tryouts are being applied more often. Training necessities will likely arise to align current military AM operators with existing and developing standards as well as adapt them to the military context, quality management aspects, e.g. defect identification, and how to handle qualification, certification, and standardization in critical scenarios. Furthermore, we contend that a new method of AM electronics, should be integrated into AM practices. For example, the mesmeronic process chain, developed at the Fraunhofer Institute for Additive Productions Technology, offers several advantages: integrated conductor tracks which require fewer or no cables, embedded electronic components which reduce assembly efforts, a lightweight design which demands less material, and the possibilities of many varieties enabling rapid development. With the use of carbon fiber reinforcements, a certain shielding against EW can also be achieved. The use of AI in production offers a range of potential applications through data-driven design based on genuine data, such as enhancing design and improving materials and processes. In the manufacturing process, accuracy, speed, and simplicity should be increased. Hence, the scrap rate decreases, and tolerances are reduced for higher precision components. Data-driven decisions will follow, e.g. machine settings, pathway planning, post-processing precision, and quality control. Ultimately, the cost per unit should be lowered through AI-driven decisions. Research has confirmed that AM reduces costs and is economically sound. However, most applicable critical items are not produced by AM, e.g. microchips, cables, antennas. In Ukraine, the role of AM in combat conditions is to produce fittings, modifications to drone structures, and casings for grenades with a high weight damage ratio, as well as fins for homemade bombs. A major AM production line based on the available 3D printers close to the front cannot work at present, as drones are generally not delivered to combat units without prior flight testing, which cannot be done at the front. Aspects to be considered for decision-making. Current drone designs show that most parts can be pre-produced or stored without the danger of obsolescence between production, storage, and potential use. These parts can be counted as the frame, the propellers, the motors, the battery, the antennas, the electronic speed controller, the flight control unit, the video transmitter receiver, and the camera board. However, the GPS and radio control transceivers need constant updates. The frame, if pre-produced, has to have the ability to mount different fittings, and the printed circuit board and flight stack have to have the ability to host different and adapted controllers. Components are the main costs associated with setting up a traditional drone manufacturing business. These can account for 30 to 50% of total manufacturing costs. Skilled labor is also necessary, and this can consume 20 to 25% of operational costs. The maintenance and repair of the machines and tools can run up to 5 to 10% of operational costs. Logistics and shipping add another 5 to 10%. Renting a facility can add another 10 to 15%. However, minor positions would be research and development, quality control, marketing, insurance, and other overheads. Of course, several more technical questions connected to traditional manufacturing as well as AM will be of importance: the lifetime of equipment, the assumed minimum shelf life of materials, how weather and climate conditions influence the performance of equipment and materials, the mobility of the equipment and materials, the reliability of supply of equipment and materials, the maintenance intensity of equipment. Other areas are the manufacturing strategies, e.g. product design, manufacturing practice, supply chain and logistics planning, e.g. centralized, decentralized production and distribution, lot sizing and inventory management, sustainability, materials, energy consumption, and the balance between depot and field-level maintenance. Cutting-edge, affordable, ready. Historically, war has been a continuum of constant change, which drives technological innovation. This applies equally today. In the field of military production, the need for customization, increased product functionality, and rapid prototyping, as well as full production chain competitiveness, must be quickly achieved. Consequently, production must be simplified, robust and deployable, or integrated into existing units, including ships and planes. The business model has to adapt to mass and customized production. The maturation of AM has the potential to play a role in such a new manufacturing ecosystem. However, an AM-based manufacturing system or even a lights-out, factory-based model is neither feasible nor meaningful for drone production at present. As initially pointed out, outside of Ukraine, field manuals have not yet included the art of drone warfare, people are not trained, and drones are not introduced in large numbers. Yet, there is a massive production capacity as well as know-how in terms of technology, application possibilities, and active use in Ukraine. Conceptually and doctrinally, introducing drones should go in parallel with a massive increase in the number of drones available to armed forces. This could be done by relying on production capacities in Ukraine. Systems can be ordered in Ukraine, where strong investments in the domestic defense industry by German companies already exist. Additionally, in modernizing European drone forces, supply and training contracts for soldiers and systems are needed urgently. They can also be realized by transferring current knowledge from Ukraine to other European countries, such as Germany, where certain companies already have working relationships with their Ukrainian counterparts. There are several advantages attached to this kind of procurement. First, there is a lack of regulation in the area of drone production, which allows the quick scaling of efficient and cost-sensitive production. One does not even need any license to start producing drones and sell them. It is enough to register a company without any other permission needed. Second, the necessary workforce can be hired with service contracts without permanent employment, which allows businesses to appear and develop without high risks. Third, there is a lack of bans on flight tests, which are necessary and part of the production process. Fourth, any drone produced is counted as civilian production as long as no ammunition is attached, which enables faster export. Fifth, there is a lack of IP restrictions in the production of drones. Because of the war, drone designers are patenting their drones. Ammunition containers, small parts, and even long-range drones are already manufactured through AM. However, this production method is not suitable for one-way attack drones. In addition, there is a need to start ordering critical parts that cannot be produced by either Ukraine or Germany in order to create a strategic stockpile. Right now, the existing supply chain from the PRC, US, and Taiwan is intact and can be used. However, those supply chains cannot be taken for granted, so self-reliant production capacities for those parts must be developed. As the outcome of the war in Ukraine is also unpredictable, a production capacity for all parts of drone manufacturing must be developed domestically. These production capacities could and should integrate AM into the manufacturing ecosystem. In the case of the need for domestic drone manufacturing on a massive scale through AM, intensive relationships between producers using AM, materials suppliers, and OEMs have to be established. A materials ecosystem with an open materials license and a contractual agreement with the OEM to buy tokens, digital spare parts for printing. or the digitalization of existing components, including the recertification of components, will be necessary to build up a digital inventory. In this respect, NATO has already achieved standard leadership. Furthermore, batches of experimental verification platforms in areas like key materials and major equipment need to be constructed. The provision of economically viable production capacities to such an extent, preferably with fixed quantities, can be achieved through the introduction of indefinite delivery, indefinite quantity contracts, whereunder partial orders can be placed and which compensate for idle capacity costs and serve as a kind of reserve capacity payments. As a consequence, significant first-mover advantages could be realized while at the same time living up to the slogan, cutting-edge, affordable, ready. Authors: Dr. Wolfgang Müller is a senior resident research fellow at the German Institute for Defense and Strategic Studies. His research interests include total defense, China, and the weaponization of economics. Dr. Sergej Sumleny is the co-founder and general director of United Unmanned Systems LLC, a German-Ukrainian drone developer and producer. He is also the managing director of the European Resilience Initiative Center. The views contained in this article are the authors alone.
This was the Horizon Audiofiles, a podcast of the Defense Horizon Journal. For more information, go to www.tdhj.org. Thank you for listening.